So in this video, I'd like to explain the key rate shift technique by explaining Bruce Tuckman's table 5.2, which is the exhibit he uses to introduce the key rate shift technique. If we understand this table, this analysis of key rate shifts, then we basically understand the key rate shift technique, and we will see why we do it. Why we do it briefly is that if we had a portfolio manager and a more typical duration analysis, she might hedge or neutralize that interest rate exposure by determining that the appropriate duration is, say, 7 years. And in fact, that will be a good hedge, but only if the term structure shifts in parallel. That's the implicit assumption of the single factor risk measure called duration. It implicitly assumes the term structure shifts in parallel. So she neutralizes with the duration of 7 years, then she will be protected if the term structure in fact shifts in parallel. But what if it does something else like steepens or twists? Then actually the duration won't work. Enter the key rate shift technique, which in this case, in the table we'll look at, takes that term structure, selects only a limited number of key rates, in this case 4, so that we have 4 regions. Then the analysis here, instead of a single duration, will produce for us 4 key rate durations, and our portfolio manager can instead to design a hedging portfolio with 4 different securities that now will be protected in many scenarios where the shift isn't parallel. For example, maybe the term structure suddenly steepens so that the 30-year interest rate jumps more than the short-term interest rates. Well, because the portfolio manager has used a key rate shift technique, her hedging portfolio includes protection against a 30-year shift or that region. So we have a whole term structure out to 30 years, but we've basically divided into 4 different regions in this case, where each region is really anchored on a key rate, 30, 10, 5, and 2. And so that's the key idea, is to overcome that limitation of the single factor risk measure duration by using a multi-factor approach here, the key rate shift technique. So I look forward to explaining this table 5.2 in Bruce Tuckman. Before I show you and try to explain Bruce Tuckman's first exhibit on the key rate shift technique, I think it's worth reminding or explaining why we're even doing it. After all, the key rate shift technique is more complicated and difficult than the duration analysis that we've previously looked at. If we're following along in Bruce Tuckman, we are transitioning from single factor to multi-factor approaches, and it's easy to lose sight of why we're even doing this more difficult analysis. The reason we're doing it is that we're overcoming the limitation of the single factor risk measures. Recall they are duration and DV01, that's dollar value of a basis point, also called price value of a basis point. I think it's a little more intuitive, PVBP, right? That's the dollar change that would be implied by 1 basis point shift in the yield. So those are the measures that we've been studying, and they are single factor risk measures. And as single factor risk measures, they are convenient. Their key limitation, however, is that they implicitly assume a parallel shift in the term structure, right? And to illustrate that, what I've taken here is I just made these up, 3 different term structures. I've deliberately got different shapes to them. And what we just want to imagine that we're pricing, I arbitrarily selected a bond. You can see here, this is years on the x-axis. So it's a 30-year bond, and in all cases, it's a 3% per annum coupon that pays semi-annually. So it's paying 1.5% of face value every 6 months. Those particulars don't really matter. But here in the spreadsheet below this graph, what I've done is compute the associated price and yield according to 3 different term structures. Right, I have both yield and price for each of them because in a certain sense, they're functions of each other, right? The lower the price, The lower the price, the higher the yield, as you can see here. So the idea that I wanted to impart relative to this limitation is that we could take each of these three term structures in turn. Let's start with the easiest one of all, right, is the one in blue. And oftentimes on an academic exam type setting, this is the assumption we would get, a flat yield curve at 4%. And you'd read the flat yield curve. But that's a little bit deceptive because a yield is already just a single factor. So what we really mean is a flat term structure, as I've illustrated right here. And that means that what I'm plotting here, what am I plotting? It's not actually labeled here, but what I happen to be plotting is spot rates, which also be called zero rates. So that's what I mean by term structure. Term structure has rates. In this case, see the little dots at every 6-month interval over 30 years. I have 60 different spot rates on this. That's what I mean by a term structure. It's a series of spot rates. The yield's not like that. The yield's just a single factor that really incorporates all the information of the term structure. So with a flat term structure of spot rates here at 4%, if I go take this 3% coupon bond, the details of that calculation aren't that relevant. Its price will be $82.71. And after all, we do, just sort of as a gut check, we do expect a discount to par because the yield is greater than the coupon. So if the scenario is a 4% flat term structure of spot rates at 4%, the price of this 3% coupon bond happens to be $82.71. Okay. Now, if I take another term structure here, the green one, this may be a little more realistic. It's upward sloping. Same exact bond, right? Same exact cash flows, but now it's not flat. So each of its cash flows is getting discounted at a different spot rate. You can see a progressively upward sloping term structure here implies that this 30-year, this bond, its final cash flow, that final coupon and par value is discounted as much more than it would be under the flat term structure assumption. Okay, so under that scenario, the same exact cash flows associated with the bond imply a price of $59.02 and a significantly higher yield of 5.97%. And finally, I made up a sort of wacky term structure here that does a little bit of both, and it has a price of $63.85, corresponding with a yield of 5.48%. So here's the point about the limitation. When we use duration or price value basis point, these are necessarily single factor risk measures. What we are doing is we are shifting the yield assumption, and regardless of the term structure, what that means is it's implicitly a parallel shift in the term structure. That's the key phrase. The limitation is the assumption of a parallel shift in the term structure. Very easy to miss this fact. So even for the goofy one here, when we use duration or any of these single factor measures, because we're using a single factor, only one variable to describe the shift, if we're shifting it up, then really implicitly, it's still a parallel shift. I mean, my shift here is more dramatic than 1 basis point, but just to illustrate, it's still a parallel shift. After all, we're talking about yield. How else could we describe a shift in this term structure with only a single variable? If you think about it, we've only got a single variable. We're only shocking a single variable. That's the yield. A parallel shift is the only thing that really can be implied. Even if we think about the flat curve here, anything else, a steepening or a flattening, would require us to use more than one variable to describe the shift. So that's the key idea. We're leaving the simplified world of the single factor risk measure where we are using a yield, and with duration, that yield shock is the single factor really summary of the term structure that is being shifted, and in doing so, we are assuming that the term structure shifts in parallel. And so we know that's not necessarily realistic, and that's why we have the key rate shift technique. So what I have here is my recreation of Bruce Tuchman's Exhibit 5.2. My numbers don't match exactly, and that's largely because I have a round 4.5% par yield curve that is flat, as opposed to, I think his number is slightly different than that. So, but otherwise, directionally, my results are consistent, and I do perform the specific calculations, including the interest rate factor that I've used here. I followed him is I've used a par yield, which adds a level of sophistication to this analysis that I don't want to go into now. But the point is that in the key rate shift technique, we have an interest rate factor, and we could decide what specific type of interest rate factor we want to use, right? We've seen that before. An interest rate factor is a generic concept, and then we might have to decide, in this case, we decide which kind of interest rate factor are we going to use. Will it be a spot or zero rate? Will it be a forward rate? Well, none of those in this case. In Tuchman's case, it's a par yield. That's the specific type of interest rate factor that is being shifted in the analysis. And so what he has here is a 30-year C-strip. So that's just a 30-year coupon bond. That's the easiest part of it, right? It's only a single cash flow at the end of 30 years, no cash flows in the meantime. So our coupon is zero, and a par yield curve that is flat at 4.5%. So there are 60 semi-annual periods, and then we have an initial price for this. It's also straightforward. In my spreadsheet, I simply use the Excel's PV calculation. Zero coupon bond, we expect it to be pretty aggressively discounted, so it is. So the initial price of this 30-year zero coupon bond at 4.5% with semi-annual compound frequency is $26, and you can see about 31.5 cents. Now we get to the essence of the key rate shift technique, and this happens to be Tuchman's example, but there are a lot of decisions that the user can make. There's a lot of design decisions, so there's no one magic way to go about this, but including there's a choice as to how many key rates. But the idea here is to select a limited number of key rates that cover the term structure so that we could approximate that term structure with the multi-factor model here. But we don't want to use we don't use too many rates. There's no need to use 30 key rates for a 30-year term structure. Tuchman's example here uses only 4. So the key rates are 2, 5, 10, and 30. I've graphed them here. Here's my 30 years timeline or term structure on the x-axis. And then the y-axis here, I followed Tuchman with, the y-axis here is really just basis points. 0 to only 1 basis point. So that's only 1 basis per point, right? That's really a very small amount, 0.01%. And so then the idea is, instead of a single factor where we might shift or shock the entire term structure in parallel by 1 basis point, which would be more along the lines of the DV01, here we have the 4 different key rates, so we divide the term structure up into the key rates and the neighboring key rates that are in the region. And I've color-coded them here, so I have a 2-year shift, and so you can see the 2-year, these are 30-year periods here, so the 2-year is really right here. The 5-year peak is right here at the peak. The 10-year is right here at the peak, and here's the 30-year. So it's only the 4 key rates. Take that out, put that back here. 1, 2, 3, 4. And then the neighboring rates, and these lines here are just governed by a simple interpolation rule. So for 2 years and less, we stay at the 1 basis points, and then there's a interpolation going down to here at the 5 years, because that's where the 5-year key rate exists, and it has its own interpolation from 0 at 2 years up to 1 basis point at 5 years. And so in blue, you can see we have the 5-year key rate, and its neighboring rates all do experience a shift. So these lines describe the shift, and the shift only maxes out at 1 basis point, but you can see neighboring rates here experience some shift in rate as well. If that seems confusing, then here's a concept that may sort of glue it together, and that concept that is the following. If we shifted all 4 simultaneously, what would we get? What we would get is every rate here in the term structure would shift exactly at 1 basis point, right? If we think about that, well, here's a point, here's a neighboring rate, a rate here in the middle. It's halfway between 10 and 30, so this is actually at 20 years. It's neighbor to both the 10 and the 30-year, and if we shifted all of the key rates, therefore including the 10 and 30-year, what would happen here, this neighboring rate, it's at half a basis point at the intersection. It would get half a basis point shift due to the 10-year, and also another half due to the 30-year, and collectively then it would be at 1 basis point. And you can see similarly any of these points here, neighboring rates, when you add, if you included both shifts together, you would get 1 basis point. So if we shifted them all simultaneously by 1 basis point, we should get the same effect we would get on a DV01, a parallel shift of 1 basis point. But in terms of the analysis, what we're doing is we're taking them each at a time. So you can see the analysis has 4 rows, and it's 1 for each key rate shift. So if I just pick on the 10-year key rate, because it's sort of clean in the sense that I have the 10-year key rate is the peak, and that it has linear interpolation down to 0 at 5 years, the next key rate neighbor, and similarly interpolation down to 0 at 30 years, the next neighboring key rate. If we just take the 10-year shift here, what the analysis does is, instead of in our single factor model where we shift the entire term structure in parallel, all we're doing here is this shift. We're shifting this region, which runs from 5 to 30 years, because 10 is the key rate, and we're going down to 0 at the 2 neighboring rates. So you see how we're leaving out this part of the term structure, but all of the other rates are getting shifted. And the y-axis here is the 1 basis point shift. So if you just add 4.5% to this, then you're getting the actual par yields that we're using to reprice the bond. So that's the technique really, right? If I'll say it one more time, because it's difficult, we're doing it for each of the key rates. We're saying, okay, start with the flat 4.5%, but then just for the 10-year rate, for example, just shift its key rate and all the implied neighbors, so it's just a shift in the key rate and its neighbors, and then reprice the bond to figure out, well, what's the effect of a 10-year shift? Similarly, so that takes up more of the region. Then let's say just the 2-year shift, you can see, is much more modest. For the 2-year exercise, it's just, okay, we start with a flat 4.5%. Now let's just shift the 2-year key rate up by 1 basis point, just 1 basis point, and whatever neighbors get dragged along per the rule, right? These neighbors, everything less than 2 years, and then everything, all the rates from 2 to 5 years. So that's the shift. In that repricing, the rest of the term structure gets left out. What would happen to the price if we just shift to the 2-year rate and its neighbors? And so in that way, it's a repricing exercise for each of the 4 key rates plus neighboring regions. We start here with an initial value of pricing this bond at a flat 4.5% is 26.31. And then below here, as part of the spreadsheet that I certainly won't go into detail, is I do the repricing, right? So here for the 2 years, all I've done here is I have the shock, and in green is that initial part of the term structure that's affected. So you can see here for the 2-year key rate shift, my par yield for that region, see how these are higher than the 4.5, but then after that, after really here, the 5 years and beyond, I haven't changed anything about the 4.5% par yield assumption. The rest is flat. Similarly, if I go over here to 5 years, this is just for the 5-year key rate. Notice my par yield is 4.5%, and then when I get, oh no, I'm sorry, yeah, for 5 years, oh yeah, it's 4.5% until I get to the 2-year mark, because that's the neighboring rate, and then it starts to go up because now I'm in the region for the 5-year key rate, and then it's peaking right about here, and then back down again. So I've actually got a mistake in here. I'll uncolor that because I don't mean to. That's actually not part of the region. But this is part of the shocked region where you can see I am changing the par yield, but it's the only part of the par yield. And then that par yield translates into discount factors that come up here and reprice the bond. So that, because Tuchman used a par yield, it complicates that analysis, but suffice it to say, all that we're doing here is repricing the bond at given respectively in each scenario of what we've visually shown here, a shock to the key rate and then dragging along all its neighbors per that linear interpolation rule. And so the 30-year one is maybe the most intuitive, or which matches what we would expect, and that is to say, here's our initial value of $26.31.5, and then if we go and shock that term structure per this key rate here, pulling up the 30-year key rate by 1 basis point, and then all of these neighbors going down to 10 years, right? So that's really 20 years worth of neighbors, are actually, I guess, 40 data points here, 40 rows on the spreadsheet. And then reprice that bond so we're unaffected everything 10 years and below. The price of my bond would drop to $26.20. And I'm going to move this up, get this back here, get the calculations out of the way. And what I've got here then for the key rate is just a simple difference. But there's a negative in front of it, and that's analogous to the negative that we saw in the DV01. After all, the key rate is directly analogous to the DV01. And here you can see at the 30-year shift, my key rate 01 is a little bit above 11 cents. And what it's saying is that it's a positive value. And it's saying that if we shock the key rate up positively by 1 basis point, then we get a decline in the price of the bond of about 11 cents. The other negatives are probably less intuitive. Tuchman has to go into a technical digression on that, and I won't do that here. All just to say that we do have a negative in front here, so if we have a positive value, it's directionally similar to a positive DV1 and duration that are more typical that we expect, and that is the inverse relationship between price and yield. Yield, in this case, par rate goes up, we expect the price to go down by 11 cents. And the key rate duration is also similar to the regular duration, except it just applies to that region of the term structure instead of the whole term structure. And we can think there, in terms of analogies, are maybe the most important function for the regular DV01 was that the duration times price, its duration times price, which itself is dollar duration, divided by 10,000, equals the DV01. Well, similarly, the key rate 01 is equal to the duration, where I'm going to just subscript the K to indicate it's a key rate duration as opposed to a plain old single factor duration, times the price divided by 10,000. And that means that this key rate duration here, it's solving for this key rate duration. So that's implying that our key rate duration is equal to the key rate multiplied by 10,000 divided by the price. So that's the formula that I have here. And it's really not maybe as hard as it sounds, because what are we doing here? Well, what's that key rate 0.1? Well, remember, that's the dollar change if there's only a 1 basis point shift. Well, and a 1 basis point multiplied by 10,000, right there's 100 basis points. The 10,000 itself is 100 times 100, the 100 basis points in 1%. And then 100, 1% in 100% or 1.0 unit. So this is just rescaling the key rate 0.1 into something that's more like a dollar duration. So what we have in the numerator here would be a dollar price change, and we're dividing it by percent to get the key rate duration, which is really a percentage. Or I might say could be used as a percentage, right? So if I'm going to strip this out now. The 43.07 here as a key rate duration is analogous to a regular duration in the sense we could say if the key rate were to shift by 1%, then we would expect the bond price to change by about 43%. We multiply that percentage change in the key rate by this number to get an estimated percentage change in the price. And so it's a very high number here at 30 years, of course. But you can see formulaically, that's all that I did. I take the key rate, I multiply by 10,000, and I divide here by the initial price. So that if I come back here to the summary, the summation here, that's significant because if I add these together, then visually what I've done is I've shocked all the key rates visually per this rule simultaneously, which again shifts the entire term structure in parallel by 1 basis point, such that the summation here of these key rates, we should expect it to equal the DV01 or it should be very close to the DV01. Actually, we wouldn't expect it to be exactly the same, but it should approximate the DV01. And similarly, this key rate duration here, the sum of my key rate durations here should approximate just the plain old duration, but we don't expect it to be exactly the same. The total line here is significant because it reconciles, and conceptually it tells us, yes, that if we shocked all the key rates simultaneously, we should get a result similar to, very close to, a parallel shift. So it's useful for reconciliation purposes. However, that's unlikely to be the scenario that we would imagine or use to hedge against, because that's precisely why we departed from that single factor risk measure of duration to these multi-factor measures. What I mean is that we've carved the term structure up now and characterized it in multi-factor fashion with the 4 key rates, precisely to overcome that limitation of a parallel shift. And so now that's why Tuchman uses this then as the platform to go and hedge with several securities, because the idea is that now we can make a decision to hedge with a replicating portfolio and protect ourselves against non-parallel shifts. If we have a portfolio that hedges us against all these 4 key rates and the term structure shifts, let's say it twists or it steepens or it flattens, but it does in a way that can be approximately captured by the key rates, will still be hedged for that non-parallel shift. So that's the whole point in doing this, is to allow ourselves here a multi-factor approach where we still acknowledge the reality, still the economics of a 30-year term structure, but we have a limited number of key rates that we could hedge against that, while wouldn't be perfect in a non-parallel shift, they might do the job well enough in a non-parallel shift. So that's at least my attempt to look at Tuchman's 5.2. As usual, if you stayed with me this long in the video, but it's helpful, please subscribe to the channel and you'll get update as I continue in the series. Thank you.